Hello. I'm going to tell you today about the entry-specific matrix estimation under arbitrary sampling patterns through the lens of network flows. This is joint work with Yudong Chen from UW-Madison and my student Shumei Shi, who graduated from Cornell earlier this year. Consider a matrix estimation task where we would like to estimate a signal matrix M star, which is an n by m matrix, given partial and noisy observation. In particular, consider here that we add additive noise, denoted by this matrix E, and that additionally there is a sampling mask denoted by this matrix omega. So the challenge is that this sampling mask or the observation pattern can be highly irregular and unstructured. In the previous literature, typically they assume that either a sampling pattern arises from a approximately uniform sampling model, or that this sampling mask satisfied highly structured properties. For example, there exists some dense submatrix that can be used to estimate the entry of interest. In the general setting, when we have completely arbitrary sampling patterns omega, we should not actually expect uniform error. This is because naturally there are some regions of the matrix which are very densely observed and others that could be extremely sparsely sampled. As such, our goal should be to get entry-specific guarantees. In particular, we would like to know, as a function of the sampling pattern omega and as a function of a particular entry in the matrix, can we understand the hardness of estimating that entry as a function of the observation pattern? In full generality, this is a very difficult problem, but we are going to consider two very simple models in which we are able to give very clean insights. So the first model is that of an additive model. In an additive model, the signal matrix satisfies additivity. In particular, M star Ij can be written as a sum of A star Ij, which is a row fixed effect, and B star J, which is a column fixed effect. In fact, these additive models arise in econometrics, in particular in the setting of panel data analysis, and they refer to this model as a two-way fixed effect model. In this setting, one typically assumes that you observe the outcomes of a set of units across time, and that the outcome is a sum of a unit fixed effect, denoted here by alpha I, a time fixed effect, denoted here by gamma t, and that there is some individual causal effect, beta it, which is turned on when the treatment variable xit is 1. We will assume the assumption, we will use the assumption that the individual causal effect itself can also be written as a row fixed effect, a row causal fixed effect, mu I, and a column causal fixed effect, nu t. Under this assumption, the data can be thought of as represented in two matrices. One matrix corresponding to the data observed under control and the other corresponding to data observed under the treatment. And under the control and treatment, respectively, the expected matrices both satisfy additivity. So as such, you can think of the task of causal inference and panel data analysis as the task of estimating an underlying additive matrix given sparse, noisy observations. The second model we will consider is that of a rank 1 model, where the signal matrix satisfies M star Ij being the product of a row fixed effect A star I and a column fixed effect B star J. This is also called an interactive fixed effect model. These kind of models arise also in other application settings, such as Z2 synchronization, where these latent vectors, A star I and B star J, take values in plus minus 1. And the observation model is additive Gaussian noise. And another setting is that of crowdsourcing, where we consider binary tasks that have a ground truth, Q star J, that is plus minus 1, and worker reliability, denoted by P star I, which takes values between 1/2 and 1. This worker reliability represents the probability that worker I answers the task correctly. Let M star Ij, then the observed data, denote the worker task response. Then this expected matrix is a rank 1 matrix. In particular, it's 2 times P star I minus 1 times Q star J. Under both of these types of models, additive models and rank 1 models, our approach is going to build a connection, is to build connections to network flows. In particular, we will show how network flows will be used to construct estimates for each entry in the matrix. And furthermore, in the setting of additive models, the network flow estimators in fact recover both the difference in difference estimators and two-way fixed effect regression estimators, which are the two most commonly used estimators for these two-way fixed effect models in panel data analysis. So let's start by just taking a step back and reviewing what is the problem setup that we're trying to solve in the additive model setting. So again, we want to estimate a signal matrix M star given partial and noisy observations. And the key assumption is going to be that the signal matrix M star satisfies additivity. In addition, we will allow the observation set omega to be highly irregular and structured. In particular, we are going to have all of our results conditioned on omega. And so we will allow any arbitrary omega. This additive noise matrix E contains independent Gaussian noise for simplicity. This can be slightly relaxed to independence of Gaussian or even dependent noise terms, but in that setting, some of our results will need to be relaxed a little bit or are a little bit looser. The goal is to find a simple and statistically efficient algorithm that provides entry-specific error bounds for our estimate M hat that identifies the hardness of estimating each entry as a function of that arbitrary observation pattern. All right. So as I alluded to, the approach is going to be to draw the connection to network flows, but what is the network that we're going to be considering? So we're going to construct a bipartite graph that reflects the connectivity in this, it reflects the sampling pattern as in the observation set omega. In particular, the left nodes of the graph represent the rows, the right nodes of the graph represent the columns, and there's a edge in the graph if there is an observed data point in that corresponding entry in the matrix. So you can just think of this matrix omega as the adjacency matrix for this corresponding bipartite graph. Now, suppose we're in this particular example, we want to estimate entry 1, 1. So that corresponds in the graph to the pair of vertices U1 and V1. And so we're going to estimate M star 1, 1 by finding a path from U1 to V1. In this case, there's one path. It goes from U1 to V2 to U2 to V3 to U3 back to V1. And given this path connecting U1 and V1, we construct an estimate by alternating adding and subtracting the entries of the edges along the path. You can see very simply that this in fact leads to an unbiased estimator. So if we write the expectation of each of these entries, you can see that the latent fixed effects that associated to the intermediate nodes in the path just cancel out, such that at the very end, we can see that this alternating add and subtracting estimator, we refer to as the difference on path estimator, is indeed unbiased. And so the expectation is the sum of the fixed effects corresponding to the endpoints. Okay, so since we can construct an estimate giving a single path, it's natural then to ask how we can construct estimates given general flows, since flows are simply just convex combination of paths. But then there becomes a question of what's the optimal way to combine estimates across different paths. It's very natural to average your estimates, but in this example on the right, you can see that when your paths could be different length, clearly you probably don't want to average them evenly because longer paths have more noise. Additionally, you could have settings where the different paths have overlapping edges. So in this particular case, there's two paths, but they both overlap in the purple edge. And so again, you can ask, well, what's the optimal way to combine the estimates? So what we do is consider a general unit flow, F, from UR to VJ, and the corresponding unit flow estimator simply weights the data in the data set proportional to the corresponding weight in the flow. And if you can think about it, that as long as the nodes are ordered, and you'll order the left rows before the right nodes, it will in fact turn out that this flow will alternate in signs. So we can clearly see that because the noise is zero mean and due to full conservation, this estimator for any unit flow is indeed unbiased. You can also see this by recalling that a unit flow is simply a convex combination of paths. And so the unit flow estimator is simply a convex combination of each of the path estimators. And we know that every one of these path estimators is indeed unbiased as well. So you can ask which is the optimal flow. It turns out that the optimal minimum variance flow is the electrical flow. And this electrical flow, we'll see in a moment how it arises, but the variance, the variance achieved by this electrical flow is in fact the effective resistance. And we can see in these two examples here that the electrical flow, in fact, allocates higher weight to shorter paths, and also it on the setting on the left where we have two paths that share one edge, it simply shares the weights on the red and blue edges and then puts weight 1 on the purple edge that's shared. Okay, so let me explain the intuition of how this connection arises. So consider your graph and view every edge as a resistor with resistance 1. You can use this then to construct an electrical network. Then suppose we attach a battery to nodes Ui and V1, and then we attach this battery to send a unit of current from Ui to Vj through this electrical network. This results in a current referred to as the electrical flow. Now, the electrical flow is going to be the unique unit flow that minimizes the energy of the flow. And it turns out that the electrical energy of any general flow can be written as a sum of these quadratic in the flow terms, in this expression that's quadratic in the flow terms. And so you can, by seeing this, you can see that, in fact, there's a direct relationship, in fact, it's proportional to the electrical energy of a particular flow and the variance of the corresponding flow estimator. This is because the flow estimator is simply linear in these flow parameters, and the energy of the flow is quadratic in these flow parameters. Thus, the energy minimizing flow is equivalent to the variance minimizing flow. Now, the effective resistance is the potential difference, so the amount of voltage that you need to apply between Ui and Vj in order to induce a single unit of current. This effective resistance measures how connected Ui and Vj are. So if Ui and Vj are connected by many short paths, this effective resistance is low. And if they're connected by a few long paths, the effective resistance is high. There's another way to interpret the effective resistance. In fact, it's proportional to the expected commute time between Ui and Vj. Again, capturing a notion of connectivity. So what can we show about the electrical flow estimator? I already alluded to our upper bound. We can show not only is the electrical flow estimator unbiased, but its mean squared error, or its variance, is proportional to the effective resistance. Therefore, its mean squared error is also bounded above by a quantity proportional to the effective resistance. In addition, we can actually use the voltages of the corresponding electrical network to show a minimax lower bound, then no estimator can achieve a mean squared error that's better than proportional to the proportional to the effective resistance. So this shows that, in fact, our estimate, the electrical flow estimator, is minimax optimal, and this is an optimality that holds for every entry ij. Furthermore, interestingly, we can show that this electrical flow estimator is in fact equivalent to the least squares estimator, which is obtained by finding the A hat and B hat vector, these latent fixed effect vectors, that minimizes the least squared loss, and then estimating M hat ij using the sum of A hat I and B hat j. This implies that the estimator is also the uniform minimum variance unbiased estimator. So if we apply this approach for our example or motivating example of a panel data with two-way fixed effect model. It shows that we can estimate the individual causal effect beta IT simply by estimating the outcome under treatment that's denoted by G hat IT, subtracting off the estimate of our outcome under control denoted by F hat IT. And this means that the causal effect beta IT is identifiable if and only if this pair of vertices, UI and VT, are connected in the treatment and control graphs. Furthermore, it gives a very clear error bound, entry-specific error bound for this individual causal effect that is a function of the sum of the effective resistances in the treatment and control graphs. And this shows that a variation of these two-way fixed effect least squares regression is in fact equivalent to electrical flow estimator, thus arguing that it is in fact statistically efficient for these individual causal effects. Additionally, we can show that this very popular used difference in difference estimator is also a flow estimator, simply using lane 3 paths. So what is a difference in difference estimators? It assumes a very specific treatment pattern where I have the treated units and control units, and a pre-intervention period and a post-intervention period. In the pre-intervention period, both units are placed in control, and in the post-intervention period, only the treated units are treated. The difference in distance estimator computes the difference in the post-intervention outcome minus the pre-intervention outcome of the treated unit, and then subtracts off the difference in the post-intervention outcome minus pre-intervention outcome for the control unit. By rearranging these terms, we can show that the difference in difference estimator, in fact, can be written in this form. It's a difference between yi2, which is the outcome of the treated unit in the post-intervention period, minus these three terms, yi1 plus yj2 minus yj1. In fact, we can see that those three terms really arise from the network flow estimator corresponding to the lane 3 path in the graph associated to outcomes under control. So in particular, I'm depicting here the graph associated to this control observation set, yi1, yj1, and yj2. And if I want to estimate the outcome of control of unit I at time 2, this is an outcome that was not observed in advance, but we can estimate it using the path from I to 1 to j to 2. And in fact, you can see here that this yi1 minus yj1 plus yj2 is simply the lane 3 path estimate for the control outcome of e to I at time 2. So this is kind of interesting just because it gives this network, it shows that this network flow perspective is a unifying perspective for two most commonly used estimators in the econometrics literature. So there is also some ways to extend our results to rank 1 models, as I mentioned. So in the rank 1 model setting, again, recall that we're going to assume the signal matrix is the product of a row fixed effect AI star and a column fixed effect BJ star. In this setting, instead of constructing a difference on path estimator, we can construct the ratio on path estimator. So in this example here, if I want to estimate entry 1, 1, I find a path from U1 to V1, and then I alternate between multiplying and dividing observations of edges along that path. So this estimator looks, in this particular example, looks like this, and you can see that if I were to replace each of these entries with their expected value, when there is no noise, the latent factors associated to the intermediate nodes cancel out, and I just get the product of the endpoints, which is the quantity I wanted to estimate. Of course, because there is actually noise in the observations, this estimator is not unbiased because the noise shows up in the denominator. This becomes a little bit more complicated when we think about how to aggregate estimates across paths. So, again, we want to figure out if there's multiple paths, how do we aggregate the estimates across the paths to construct a single estimate? The problem is that the estimate along each path is biased, so we can't take a simple average. So when we want to estimate M star ij, we're going to first find a collection of edge disjoint paths. Here, capital K denotes the number of paths. And for each one of these paths, we're going to remember that estimate that came from the ratio on path estimate, where the numerator alpha ijk denotes the product of the odd indexed edges along that path. And beta ijk is going to denote the product of the even indexed edges along that path. Now, we're going to combine the estimates. Instead of taking an average of the estimates, we're going to take a ratio of these averages. So m star ij here is going to be the ratio between the average of these alpha numerator terms, and in the denominator, we're going to take an average of the beta denominator terms. And what that does is it makes sure that in the numerator, if we are averaging over sufficiently many paths, that quantity will hopefully concentrate around its expectation, and that the denominator will also, if k is sufficiently large, concentrate along its expectation. And then when you take the ratio of the two, as long as the numerator and denominator separately are concentrated enough, then this ratio of averages will also perform well. So we can show that if so this k here is the kij is the maximum number of disjoint paths. It's also the same as the minimum cut, the min cut. So if kij is 0, it means there's no paths between ui and vj. In fact, we can show that this entry mij is not identifiable. Thus, we can simply consider the settings where ij pairs are connected in the graph. Then we can under the connected setting, we can show an error upper bound that the mean squared error is bounded by a quantity that is inversely proportional to the maximum number of disjoint paths, or the min cut, the min ij cut, and a quantity in the numerator that scales exponential in the maximum length of the path. And the reason for the exponential dependence is because our estimator takes a product of these noisy estimates. We can show a minimax lower bound, which is inversely proportional in this quantity k, or the maximum number of disjoint paths. By comparing the upper and lower bound, we see that the dependence is optimal with respect to k, but is suboptimal with respect to L, the length of the paths. So when is this estimator actually near optimal? Well, there's one setting in which it actually does well, is when there exists a sufficiently large, dense submatrix. So in particular, suppose I can find a k by k submatrix that contains ij. I can view the observation pattern of this k by k submatrix as a bipartite clique. So I should clarify. Suppose I can find a k by k submatrix where all of the entries are observed in omega except for ij. Then that results in a clique, and as a result, then it means there exists k disjoint paths of length 3 that connect I and j. So you could use this to construct an upper bound, and then to construct a lower bound, you would note that the minimum cut is at most the minimum degree of I and j in the graph. And if the minimum degree of I and j in the graph is proportional to the size of the submatrix you can find, the k in the k by k submatrix that you can find, then that means that the upper and lower bound would match up to the log factors. So examples from the literature where these results are tight, in fact, consist of all of these structured matrix settings that have been looked at before. In these examples, you can see that the submatrix, in fact, is the minimum size of the minimum dimension of the submatrix is equal or proportional to the minimum degree of ij in the graph. The other setting we can think about very simply would be the uniform sampling setting. So imagine that our sampling pattern comes from an Erdős-Renyi graph. Well, we can show that when the sampling probability P is sufficiently large, then we can actually consider the subgraph consisting of the neighbors of I and j. And when it's larger than this threshold, we can find a perfect matching on that subgraph, thus showing existence of Pn disjoint length 3 paths. Again, because the length of the path is constant, we can show the upper and lower bound match, since the exponential and L dependence does not hurt us more than a constant. Unfortunately, this is loose for small p, especially when p is so small that the length of the paths connecting I and j are actually growing with n. In that case, our upper bound will be could be really bad because of the exponential growth in the noise. All right. So in conclusion, we showed that if you have any given observation pattern and for any specific entry, if the underlying matrix is additive, the effective resistance in the corresponding bipartite graph is a precise way to quantify the entry-specific optimal estimation error. And this is achieved by optimal performance is achieved by the electrical flow estimator, which turns out to be the same as the least squares estimator. This allows us to show that this estimator is minimax optimal and uniform minimum variance unbiased. And it provides an understanding of two very commonly used estimators in econometrics, particularly two-way fixed effect regression and DIDs, difference in differences estimators. Some of these results extend to rank 1 matrices by considering the ratio of averages estimators, and the results are tight when it's the observation pattern is sufficiently dense, or if there exists a sufficiently large dense submatrix. But when the connecting paths in the network are very long, the result could be loose, and it would be very interesting to to study how it could be improved. Thank you. So here is the archive link of our paper. Thank you for your attention.